Yeah, it's good.
Okay, good morning, everyone, and we'll start. My presentation today is focusing on the current work devoted to modeling dynamic resilience, climate change caused natural disasters. I kind of generalized the presentation to really introduce the concepts of new concepts of resilience that we are using in this particular work. The work is related to the project that we have with IDRC, and I'll be devoting a portion of the presentation or end of the presentation to just introduce the project, but that's not the main objective. I see tremendous value in this new definition of resilience in the way how we are proposing to use that, and that will be the majority of the talk. So these are the conclusions of the talk, that in my opinion, there are practical links between disaster risk management, climate change adaptation, and sustainable development, that a reduction of disaster risk and building resilience are kind of becoming a new development paradigm, and that's the reason why this work and the focus on quantifying resilience and finding the way how that can be used in the process of reducing the risk of disasters. According to literature, according to the findings of others, there is a pretty high level of benefit that can be obtained by incorporating land use, urban and spatial planning, in disaster risk management, and we try to build on that by defining the risks in a particular way, taking into consideration the spatial and temporal variability that occurs, and making it to respond to its possible highest level of improvement in managing the risks of disasters. And obviously, I don't think for this audience this is necessary to kind of repeat. There is definitely a high level of understanding that local context of vulnerability and exposure are of fundamental value for assessing properly the level of risk and then reducing the risk. And in this formulation of the resilience that I will be presenting, we did pay attention to this kind of local context through the components that we're dealing with exposure and vulnerability. So that's how I organized the presentation, to talk a little bit more about modeling resilience, use of the systems approach as the way to achieve this quantitative definition. I'll try to clearly define the measure as we developed it, and present the kind of city resilience model, which is a tool that we are going to use and we are already using within this project, and that can be used even, I think, in a much broader context. At the end, if I have enough time, I'll give you just a kind of snapshot of the project. The project is named Coastal Cities at Risk, supported by the IDRC, $2.5 million over 5 years, with a focus on 4 large coastal cities. One is in Canada, Vancouver, and 3 other cities are Manila in the Philippines, Bangkok in Thailand, and Lagos in Nigeria. I'll finish with the conclusion that I just reviewed. I am getting over the cold, and my voice will be probably from time to time giving up, so I apologize for that in advance. When you review the kind of disaster literature, there is really no very clear procedure available today for quantifying resilience. There is a tremendous talk, and very often, I mean, if you type the word resilience, you are probably going to get millions of kind of responses, but almost everyone is defining resilience in a different way, and very often the resilience is being seen as a qualitative type of term, descriptive type of term, and I think there is a need to kind of proceed a step further and see how can we quantify this particular term in order to help us in disaster risk management. Very often, we are focusing and staying only with assessment of direct and indirect losses and assessing these losses, we feel that that's enough of kind of quantification of the risk, and then we can proceed with the qualitative definitions that are either explaining or supporting the assessment of this direct and indirect losses. My very strong feeling is that we need a broader framework. We need to go beyond only assessing the losses. I think we need something that will help us to better understand the factors that are kind of contributing to risk. And also, I think we need a procedure that may help us assess the various measures that we can use to increase the resilience or to reduce the risk. Measures adapt to changing conditions and so on. So this particular quantitative approach or quantification is aimed to help in these two areas, increasing understanding as well as giving us ability to kind of compare various options, alternatives that may reduce the risk. There are various definitions of resilience. So if you go to the literature, general definitions of cover quickly from illness, change, or misfortune to property of material, original shape, to ecological definitions are very popular due to the work of Buzz Holling in early 90s, where he introduced, and he in his work introduced this idea of multiple stable states, and through this idea of multiple stable states, he was using the resilience as the kind of ability to withstand the stresses or environmental loading and move from or shift the regime from one to another. This concept is quite well elaborated in the ecological literature, and I think it's pretty heavily being used today. This work, I think, motivated a lot the work in engineering, social, natural, and I would say engineering sciences, dealing with with hazards, dealing with extremes, dealing with the disturbances that may happen in systems. So these hazard-based definitions that you can find are going from capacity to respond to extreme event, to capacity of system, community, to kind of resist changing conditions, capacity to absorb shocks, capacity to adapt existing resources and skills to new situations. So variety of definitions without a very easy way to actually implement this decision, and find a quantitative representation of that. But there are some commonalities, and this is what I kind of extracted from the previous definitions, that most of them are identifying kind of ability to adjust to normal or anticipated levels of stress, ability to adapt to shocks and extraordinary demands, and also the time frame where we are talking about the period from pre-event preparation, planning, developing the measures to prepare for shocks, and post-event strategies to deal with consequences of the shock. So if we take these commonalities together, I think we can arrive at a definition that may help in that process of moving towards the quantitative definition of resilience. And I started looking into kind of communities, and I started kind of seeing and trying to adapt or change this definition. And in general system theory, the resilient system is the system that kind of offers opportunity for kind of development, novelty, or innovation. And that comes directly from this ecological definition of regimes. When we move from one stable state to another stable state, there is opportunity. There is opportunity for improvement. There is also opportunity for kind of decline. But the fact that these changing regimes or shifts are a consequence of the kind of resilience that's, I think, incorporated in this definition. And then moving further or focusing the definition further on to the cities, a resilient city can be kind of seen as a sustainable network or physical, and we are talking in this context constructed and natural environment systems, and human communities. I'm talking about kind of social and institutional organizations. I borrowed this graph to kind of illustrate the definition because it's a little bit modified graph based on the work of Resilience Alliance. I would suggest for those of you who are interested in this to follow this particular website. This is the alliance that is really focusing on the resilience and promoting the resilience as a measure for multiple use. But in our context, the idea is that resilience is the intersection of the various aspects of the system that I kind of try to put in definition. One is the physical environment, constructed and natural physical environment. Another one is the network or governance network that includes all the institutions, organizations, the social network that includes kind of people, human capital, equity, inequity. And the fourth one that's quite important actually including the metabolic flows, and that's what we are usually kind of focusing on in the kind of economic approach to assessing damages, only assessing damages in consequences. This is where we are talking about production, supply, consumption chains, and chains and all the aspects that may be affecting the other elements. The interaction is, the overlap of these four, or the place where they directly interact, actually goes into, I think, the meaning of the urban resilience as I would like to take it. So, you will excuse me, I get warm when I talk. So, I am kind of interchangeably using the words city, community, urban environment, so please accept that. That's what I am kind of focusing in this talk on. And I will be using this view of the city as a system of systems. There are different components, or there are different systems that are connected together within the city in the context of disasters. We are talking about essential subsystems like water lifelines, power pipelines, hospitals, emergency management organization, firefighters, police, and so on, and transportation lines. So these are all, or they all can be treated or analyzed or looked as independent systems, but when you look at the whole city, they are highly integrated and they work together. You cannot provide emergency if you don't have a free road that the emergency vehicles can kind of move on. You cannot deal with the consequence of, let's say, earthquake if you don't have enough beds in the hospitals and emergency rooms for people to be immediately treated and so on. So in accepting this definition, I think we can benefit from using the system thinking and understanding how these complex systems behave. Using also some tools and techniques that can help us deal with the complex systems. And we can also benefit from kind of coupling different existing models of various aspects of the systems to better understand the overall resilience. Please accept the fact that these are not the only subsystems. There are, many other subsystems. Many different cities may have, also systems that are not present in other cities. Everything is kind of open. But I think in the formulation and looking at the city as a kind of system of systems is a kind of conceptually important message here. So that led to final kind of definition that I'm going to use in quantifying this concept. Some work being done on quantifying the resilience was focusing on so-called identifying resilience as a performance of a system in one point in a multidimensional space of the performance measures. So in other words, looking at resilience as a single number. So you would take into consideration all the potential loads, impacts, consequences, and depending how you formulate that, you calculate the resilience, you associate that single number to your system, subsystem, component of the system, or whatever. I think this is insufficient for the proper use of this tool, and especially for helping us to understand and compare different potential alternatives, how we deal with the risk or disaster risk. So in my view is that we should be looking on the performance of the system over time. In other words, treat this particular quantitative measure as a dynamic variable, as something that's kind of changing in time. And if you look at the relatively simple example of, let's say, rainstorm hitting the city, you have a kind of time frame within which this is occurring, the intensive amount of rain that may be coming, reaching the components of the physical components of the system that should be kind of carrying that rain. So this is all changing dynamically over the period of rain and usually after the disaster for some time. And any of the subcomponents that I was mentioning may react. I mean, the dynamics of the subsystems and their response may be different. The immediate consequence of the earthquake could be the certain number of people being injured and within the buildings. The longer-term consequence may be that due to the earthquake, the water supply source gets polluted, people do not get proper or clean water for drinking, and like a month or much later in time, you get a total health response on the population that comes from the, let's say, polluted water supply. So there are very important aspects of the dynamics or the kind of change that's occurring within the system due to the disaster over time. And that's what I would like to cover and incorporate into definition. So this is our final definition, the ability, or definition of the resilience as the ability of the system to reduce the chances of shock. That is obviously set of activity, covers set of activities in advance, to absorb a shock when if it occurs, and to kind of recover quickly after the shock. So there are different ways how we can describe this type of activities, and the resilient system is therefore characterized by a reduction of the failure probability, a reduction of the consequences, lives, loss, damage, negative economic, social consequences, and the reduction of the time that's required to recover. Here's now I'm getting a little bit into this quantitative. I promised to use only 3-4 equations, not more. But this is the actually very important conceptual definition of the quantitative resilience measure. If we show on the vertical axis the performance of the system, and performance of the system could be, let's say, the quality of infrastructure, the capacity of infrastructure, the number of hospitals, or let's say the emergency services, and so various ways how we can kind of or what kind of units we can use here. The state that kind of system is in gets affected by the disaster. The time t0 will be the time of the beginning of the disaster, and the change in the system kind of performance, obviously decrease in the system performance, is that shock that disaster creates. And the time t1 identifies kind of the period until the system kind of comes back to. The interesting aspect here is I am showing in this kind of conceptual definition that we are assuming that the starting state should be reached at the end, but there are, I think, possibilities with the definition to look at that in a little bit different light. That we may actually try to deal with the reduction of the resilience with a certain set of measures in order to use this as an opportunity to move the system to a better state, so that we actually move the system back to a state that will be somewhere above this. Or if obviously there is no way to recover from the disaster in such a way, maybe end up in a state that will be below the initial starting state. But that's what the shock creates. That's what I was saying, the shift in the regime that occurs in the system due to the shock being imposed on the system. So the simple definition of the resilience is that the resilience represents the area, the red area. And in a mathematical form, this is nothing else than kind of integral. If you integrate that area over time, that's the kind of period for integration, and that's my quantitative measure.
What does Q stand for in there again?
It's any way or any type of unit that you want to use to represent the system. If, let's say, we are talking about a city, you're considering the impact of extreme rainfall. The Q could be the number of kilometers of pipes, or the capacity of the drainage system. The Q could be, in the case of the health, the number of beds you have in hospitals available in emergency rooms, the number of firefighting stations, and things. So any unit that we can use to describe the system performance.
Does it have to be a straight line?
Yes. 100? No, it's not. It's not. I mean, I'm using it as a starting state. So you can put 100, you can put number 1, you can put.
You said just a second ago that there are investments you can make, and ideally you build yourself resiliency, and you're better off at the other end. So the second half of the line could be higher.
Be above or below. Yeah. Yes. And I'll show kind of mathematically that a little bit later.
This does an excellent job capturing all of those concepts in one visual message, which is great.
Yeah.
One of the challenges, I think, in sharing this amongst the many of taking a complicated concept and challenge and sharing this is a resilience of a particular entity, like a city.
Yeah.
But how would you define that? And if I use a case where there are some homes that are getting flooded again and again and again.
Yeah.
So if those homes are acquired and it's turned into a park, that community is more resilient because you won't have people living at risk. But those people need somewhere else to live.
Yeah.
So if you just look at the value of that area, you've lost the homes, right? But if you look at the broader community, the homes are now somewhere else. People are somewhere else. We had too many people living in New Orleans. And today the population of New Orleans is half of what it used to be.
Yes.
So they never came back.
Yeah. Give me a chance to continue, and in 2 slides I'll be answering. Paul is a little bit ahead, but there is a way how this concept responds to your concept, how you transfer or how you incorporate the changes that are occurring. So, like looking the homes or a particular value of that kind of infrastructure versus the number of people that may be there or may move and change. I'll show that.
Yeah, just a minor point, but the area that you're integrating there, I mean, to improve resilience, you want to minimize that.
Yes.
Right? So what you call resilience is actually the complement to resilience, right? Because to improve resilience, you want to decrease that number.
What's
so this number value of R is better.
This number represents the area.
Yeah.
And but because I'm kind of acting here, that's taking care of that. I think what you're.
So 100 is 100% resilience.
Yeah.
So anything that takes away from that
will be lowering that. Yeah. But it's you can formulate the way. I mean, it's okay. So to finalize the concept or represent the concept in words, in the case of disasters, I selected these words. Resilience is the ability of the physical and social system to withstand disaster impacts through kind of assessment of the situation, rapid response, and effective recovery strategies. And they can be measured in terms of kind of reduced, as I pointed in the previous slide, reduced failure probability, reduced consequences, and reduced time of recovery. And this is important. This is important because that is going to be kind of used in the mathematical.
And one of the ways that this concept challenges perhaps conventional thinking is that there's more discussion at this point about maybe not having as large an impact, with how big the impact is rather than also thinking about.
I'm not yet at that stage. Okay, so traditionally we are not going into kind of mostly using this area. We are traditionally concerned about the line. Okay, so that's what the assessment of damage, focusing on economic damage or the social number of people affected and so on. So this is what traditionally is being done. Those who are thinking about resilience were focusing on this area, but determining this area as a single number. And that's, again, I think, the concept that I am trying to actually extend. And on the next slide, I'll be
I'm not sure if you're going to get into this, but you could do is you could overlay that with the sort of 4 pillars of emergency management.
Yeah.
And you have your, recovery, your response, and your preparation sitting at different parts of your line.
Yeah. I wouldn't put them on different parts of the line, but I would put them as a kind of key options, or I would say, I call them in my further slides, you will see them kind of adaptation strategies, that any measure that we put in a typical emergency management cycle provides the kind of adaptation option that will be affecting the change of this area. And this is how I would like to use this area as a measure to compare different options. Where we should put, or what should we do, how much money we should put in preparing, or how much money we should be putting in recovering and things like that. So to extend the concept a little bit and kind of introduce the extension, I need to kind of go over that to actually say that this concept of resilience is now being given 2 dimensions. One is time and space. That means that area in the previous slide is obviously affected by this timeline. If you are looking in this particular moment, you will have a portion of the area. If you're looking here, you will have this portion. If you are somewhere here, you will have the whole red area. So depending where you are in time, you will have a different value of that. The point is also, if you look at the problems like flooding, like earthquakes, like fires, where you are in space, will also completely influence the shape of this line and the red area. A particular location may be on a higher elevation and therefore exposed to the depth of flood of 10 centimeters, whereas another location may be under half a meter of flood. So there is a possibility now to add one more dimension to this, if you can imagine, like a third line, which will be space, and basically locate and develop this kind of graph in every location in space. And that's the kind of key extension, thinking extension, and now I'll show you how analytically we are planning to do that. The definition obviously needs the input in the form of these properties because they are very essential for determining that adaptive capacity. And I am kind of providing here as options the properties defined as a robustness as a strength or ability of the elements of the system to kind of deal with the shock, redundancy as a ability of the elements to be replaced, the function, if you have a pipe that connects 2 parts of the town or street that connects 2 parts of the town, is there any other way that these 2 parts can be connected if, let's say, this particular pipe or this particular road is not available anymore? Resourcefulness, that's kind of focusing mostly on the capacity to identify problems, respond to problems, organize human and other kind of response, monetary, physical, technological, informational, to kind of meet these priorities. And rapidity that deals basically with time. How fast can we provide these resources? How fast can we deal with the consequences of the disasters? Units, and this is, I think, very important. Units of the community resilience in my definitions are focusing only on these 5. We are looking at physical consequences. We are looking at health, economic, organizational, and social. But there is, if you look at the conceptual idea, there is no limit. If you feel that there are other ways to measure or other units to incorporate into definition, that obviously set can be relatively easily expanded. We focused on this because of the character of the project and the funding and the people participating in the project. We are looking coastal cities, we are looking climate change, we are looking cities that have rivers coming through. So there are physical consequences of potential flooding, there are physical consequences of the sea level rise. There are health consequences that may come, obviously, as this type of disasters. There are economic consequences that are affecting the inputs, outputs, supply chains that are providing life for the cities, organizational, the way how the services are being provided, and how this organization may affect the adaptive capacity, and as well social, like a distribution of people and different kind of groups within the areas of the city. So that list or the set that we incorporated as a units of the resilience is really determined by the focus of the project, but conceptually definition is open for any units that you may want to include. This is my presentation to kind of strengthen this idea of looking at the city as a system of systems. These are the subsystems, like I mentioned, these essential systems: water, electric, hospital systems, emergency management systems, transportation systems. And here in these blocks, I actually try to put the units and associate them with some of these subsystems. And you can see, like when we are talking about the hospital system, we would like to maximize the number of emergency points or emergency services, maximize availability of buildings and equipment, emergency procedures, infrastructure in place, minimize direct and indirect economic costs. When we are talking about transportation, we would like to maximize the transportation, have emergency procedure and so on. So we can now go into details of every of these subsystems that are forming or defining the city as a system, and put the units that you selected in the form of the criteria, that will be associated with each of the subsystems. And that leads me to a final kind of general definition of resilience. I am repeating on the top the same integral that defines the red area in my graphical presentation. And this is now basically identifying or representing or showing the extension that we actually, I think, contributed in this project. We are making our resilience first to be two-dimensional, the function of time and space, and then function of the exposure, vulnerability, and adaptive capacity, where exposure and vulnerability are coming from the potentially various type of disasters, and adaptive capacity is basically functions of the previously defined units that we are going to use in representing this. So this is why I'm saying that this is relatively open for the adaptation to particular conditions, to a particular kind of problem that you may have, and you would like to use this resilience measure. I am showing here one very important aspect, that this resilience measure can be calculated for any dimension that we selected. We can, for example, calculate this only for the health aspect, or we can calculate this resilience to, let's say, water supply infrastructure. We can use this resilience to calculate only the economic aspect. But the value of the concept is also to come up with this red area that's going to represent the mix of all these dimensions. And the proposal here is developed to kind of normalize these different impacts, multiply them together, and end up with the overall resilience. Through this relationship, I'm now putting these dimensions together. And this is the value of kind of normalization, is that we are now mixing units. We are mixing number of hospital beds with the number of dollars in damage, and that's the way how this can be pretty effectively done. I think that this kind of idea first using this concept. This concept has been present in a single resilience value measure used to natural disasters. Like some people in earthquakes were using that, extended a little bit with a kind of probabilistic way of looking at the earthquakes. I think innovation here comes from the treatment of or addition of time and space, and also innovation comes from adding dimensions and allowing resilience to be represented as a product of these different dimensions. How we are going to implement that? This is where the systems approach is helping us or can help, and my bias, my background is in systems, and I'm very strongly advocating the value of that kind of view of the world. We look at the problems as a set of components that are working together, and I think in this context we are talking about set of components. You look at the city, you look at transportation elements, you look at the buildings, you look at the people, you look at and they are all interacting within that. So the idea of implementing the systems approach is pretty natural, I think. I am proposing to deal with the temporal aspects or temporal dynamics using one of the tools within the systems approach known as a system dynamic simulation. This particular approach is based on the idea that the system structure, how many elements are representing a system, and how are these elements connected, is affecting how the system behaves. So the link between the system structure and the system behavior is very well captured by the system dynamic simulations. And building the system dynamics models, we can represent various structures and investigate through the simulation the behavior of the system. Because we are also introducing space, there is a need to somehow link this temporal dynamics to spatial distribution or spatial variability of it. And we decided to actually integrate the system dynamics models with the GIS and simply consider every point in space as one point where the detailed temporal dynamics will be evaluated. So if you can now imagine in every point you will have that kind of area of resilience, the red area kind of changing over time. And if you now represent that whole map in time, you will have a kind of dynamic map. Let's say our red area is a red color, and so now calculating in time the change of that red area in every location, you will have a map that's going to change the color and show the change in this area.
At the moment, how big are your points? Like you're going to have a defined area.
That depends on
5 meters by 5 meters, 10 meters a kilometer, something like that.
That depends on the dimensions that you are going to use. And I can tell you a little bit about the units that you are going to use. If we are just looking at the kind of physical aspects and we are talking about flooding, then going by 100 meters by 100 meters would be sufficient. But if you're looking health impact, that may be too detailed, that we do not have the information provided for health information provided. So the spatial resolution will be very much the function of the units that we are using to represent that. And let me come back to that question when I introduce the project and talk a little bit about Vancouver. You can remind me if I forget. Okay, and this is it. This is now my model. This is the model that these kind of systems form. This is our measure of resilience, which is now represented as a function of space and time. And this is, in the systems terminology, representing the kind of state variable, and the state variable is affected by, or the level is affected by the flows that are attached to it. We have two flows. One is in the form of inflow, one is in the form of outflow. The outflow is a set of impacts that are basically reducing our resilience. They may come from the climatic, non-climatic. They may come through the vulnerability and exposure that are incorporated in that relationship. And the inflows are basically the adaptive capacity represented by, various options, measures, policies that you would like to. So now this kind of relatively straightforward system diagram allows this integration and value of resilience to change in space and time. And through this kind of calculation, we can implement the quantitative measure that we developed. Obviously, this is a very high level of generalization that each of these dimensions becomes a model of itself, the health, the economic, the social, and this is exactly how we are working. This adaptive capacity may have a pretty extensive set of scenarios that may deal with the emergency management, that may deal with the planning of the city or operation of the particular infrastructure. So there are very detailed aspects that are being incorporated now in the overall modeling of the key reason, if you remember my remark, that we can use the resilience to actually observe and analyze the shifts in the regime comes from incorporating the existing conditions in the calculation. So the existing conditions are the straight line at the beginning of the red area, and we would like to see how at the end, through the calculations, the value of R will compare to that existing or the initial value. This is now more kind of techniques and programming. This concept is implemented. System dynamics simulations are giving us these type of graphs where on the horizontal axis you have time, on the vertical axis any dimension that you use to represent your resilience. And your geographic information systems are giving us chance to map and show in space the change of any variable. Like connected together, they will be supporting and providing this measure of resilience or representing the quantitative measure of resilience as defined here. That's the idea. To repeat, there are a couple of innovative points. One is considering measure to be function of time and space. So we are extending the traditional look at resiliency, making it dynamic and spatially variable. And the second key point is that through the use of systems approach and this conceptual definition, we are able to incorporate multiple dimensions of resilience into the formulation. There are no limits to the number of dimensions you would like to consider. There are no limits to various set of options that we will be using this tool to help us evaluate. The tool as it is, I'll come to your question, the tool as it is can help you by building the structure and the details of the tool, can help you better understand your system. Understand, where the sources of exposure or vulnerability, how is the risk overall being, what is, causing the risk as linked to your disaster. And the simulation or running the tools for various options can give you very good feeling, what could be the most effective adaptation option. May give you a very good feeling, what is really contributing the most to the reduction of the it may give you opportunity to, for example, compare how much you can get from the dollar invested in health service versus increase of the dike. And that's where I see really the significant value of this particular way of quantifying it and measuring resilience. Yeah. Sorry.
I think very comprehensive methodology to get to your model, and I'm a supporter of systems thinking and risk management. One area that I'd like to hear from you more on is you talked about the subsystems. You had your portrayal of that as almost a pie, right?
Yeah.
But how do you account for the interdependency between the subsystems? Right? I think that's very critical. Telecommunications with energy and so on. There's a lot of interdependencies there that add another element. How do you account for that?
This is the key. This is the key, actually, benefit that comes from this particular formulation. That when we are looking now, these impacts are going to occur within each of the subsystems. and your model will have a structure that describes the elements of the system. What is the, what are the routes that exist? What are the power lines that are bringing the energy? Where are the water mains? And so we will be able to use all these units or the measures or dimensions of resilience, how I call them, to look at actually the interaction now between all these elements. And the interactions are in that structure. So I have to show you now the graph, and it's coming. I'll show you one graph or initial graph that we are developing in the Vancouver model. So you will see. So this is a very conceptual, This graph, very simple graph, becomes a very large map of elements that are connected together, and they are kind of together producing the value that we are kind of interested in here. So you have a complete flexibility through this kind of systems approach, and especially the system dynamics, to create the structure as it is. Capture almost every element of the structure. It's your choice what you're going to look at, and it is obviously dependent on the available data and your knowledge. How are you going to represent the structure? There are no limitations in a kind of methodological idea.
You just touched on the point I was going to address, the data points coming. Where are the data points coming from to fill in your resilience values? Some are macro, some are micro in nature. Are they freely accessible? Do you have to license this stuff?
The thesis project.
Everything depends. No, you will see. I have a slide with a detailed list of data that we are now acquiring for the city of Vancouver and other cities that we are working with. Bangkok, Manila, and Lagos are doing the same in their own environment. And at the end, the models are going to be very different. They're going to use this generic concept, but they're going to be very different based on the information that you have. Because for some elements of the system, they may not have the information. We were talking with the international partners on a simple thing like what is the population of the city. Like in Vancouver, you can pretty precisely estimate that. In Manila, they don't have a clue, because during the day, that number is 1, and during the night, that number can be different for a couple of millions. And so you immediately see that the data and the availability of the data will determine the complexity of your structure. But let me come to that when I review the data for Vancouver.
And one quick follow-on to that is, does the model take into account the fact that maybe a data point is entirely missing? How does that actually affect the relative strength of the model, and can we measure that and understand that? No, this is a very valid point, and that comes, the answer to this point comes from, I think, this kind of system dynamic simulation concept, where you represent your system with a set of elements for which you have information. So your representation can be very simple if you don't have detailed information, or can be very complex if you have lots of different detailed information. To assess the impact of the simplicity versus complexity is not easy. You can actually analyze the sensitivity of these models through traditional Monte Carlo simulation. So you actually simulate the system many times, and you change, the structure. You take out piece of the structure, or you add element of the structure, and you see what the consequences are over the very large number of simulations. So I don't want to use the term sensitivity, but this is one of the way to analyze the sensitivity of your model structure on the overall behavior of the system. And the beauty of this is that in 2 days and a half, I can put the people in a stage that they can start developing models of their own. It's a very friendly type of approach, where you are working with a graphical object that represents the elements and connections between them, and you can start actually developing from a simple structure more complex structures as you find the information, as you find the data, as you increase the knowledge, and so on. So a lot of flexibility in the approach itself. Where am I? Okay. In this particular project, how am I doing with time? Okay, 10 minutes, so I think. In this particular project, we propose to look at the coastal cities, and the reasons I don't think I need to repeat to you are that, they're all suffering from the population growth, dealing with the questions of economic development, social problems, health issues, cultural difficulties, and so on. There are a number of figures, that I can use to support that. The population of the world, basically, really focusing to the cities in the future. And these large systems are now becoming obviously much more vulnerable, and vulnerabilities are coming from various sources, from economic forces to climate and so on. So the sea level rise, storm surges, flooding, high disaster risks are definitely affecting them, and that motivated this particular proposal, and we were lucky to obtain the support for this work. So the objectives of the project were to develop the knowledge base, to look at the cities and understand a little bit better, how they function, what are the risks to these climate-caused disasters, and also come up with the suggestion for adaptation strategies that will provide the best possible impact. The project is highly interdisciplinary, and I am pointing out here the difference between, because quite often people use multidisciplinary and trying to correct them. The difference between interdisciplinary and multidisciplinary is that you have subjects working on the different areas, but not kind of looking at the overlaps, and where this is the idea of interdisciplinary work, where we are really working very closely together. We have a natural scientist, we have engineers, including myself, and we have social scientists, health scientists, and economists working together. And now this conceptual definition of resilience and the development of the resilient city model became the integrative tool, became actually the activity within the project where everyone is kind of talking together, because we need to understand, how the social people will measure the, social impacts within the cities, how the economists are going to look at the impact of disasters, how the health will be measured. So really, all these discussions around the table between the partners are occurring when we start talking about a resilience model. So I was very kind of happy that we really achieved the way, or we identified the point that will kind of put us together, so that the project is not going to end up as a set of independent reports dealing with health, with social impacts, economic impacts, but it will have these reports, but it will have also the tools that will be able to kind of measure the impact, all of them, impacts of all of them together, and deal with the adaptation strategies, or analyze the impact of adaptation strategies using methods. We are in a second year of the work on this. We developed this kind of framework, definition that I presented. I kind of finished the training of the international partners. They were in April of this year here. And we are now kind of working on the detailed development of the model, integration of the system dynamics and the geographic information system. And in Canada, we are heavily now trying to populate the model with the data for Vancouver. Our kind of plan is, by the end of the year, that fully integrated generic city model is available. By the spring, that we already have a kind of functioning Vancouver model with, some data in it. And in February, we will have a next international meeting where we are going to review now the transfer of this generic model into Bangkok model, Lagos model, Manila model, and review that together, review the progress together. They do need a little bit more of our support, and obviously the differences are going to come from the available data, information, and so on. adaptation or the use of the model will be in the second part of the project, and we have people that are leading this adaptation work, which is going to end up basically in the number of various scenarios that we are going to run or simulate using this idea. These are the cities I kind of selected. Maybe I don't have enough time. Just to let you know that all 4 cities are exposed to various disasters. There are some interesting examples. Bangkok in 2011. Just pay attention to the size of the damage, how many people, how many huge disaster. And this is a really disturbing figure that about 2.5% of the national GDP was lost only in one flood event. Lagos, for example, last year again, suffering from a single rainfall that created about loss of 200 million, flooded the international airport, introduced a major disturbance to the population of the city, social, economic activities, and everything else. Manila, that you had this year 2 events, and this is one of the last year events, and I really like this picture. And the comment that I read after the disaster was, the people were asked, what did they do during the disaster, and said there was no place to hide. There was so many people, such a high density and such a high impact. They are suffering from these, typhoons that bring over the very large area huge amount of precipitation in a very short period of time. That you can see the interaction between the infrastructure and people, and how do you deal with that? This particular typhoon killed a lot of people, $300 million in damage, and my quote: "We don't have a place to go for shelter. We don't have a place to hide." Vancouver, more. Again, last year was an interesting storm. 150 millimeters of rainfall, pretty strong winds, and they canceled the ferries. The Corporation of Delta went into emergency. The BC Hydro had a number of outages throughout the city and so on. Nothing else than a pretty strong rainfall event. So that just illustrates how vulnerable are these large cities. And this selected set of kind of examples tells you the story of the importance. Okay, now I'm sorry that you cannot see this, but this is how, at the end, for example, our generic model looks like. You remember that conceptual showing only one value of resilience, input and output. So now see, when you start building the details in it, you have for example, in red here, the sector that's dealing only with the physical impacts. We now go into number of detailed variables, water quantity, quality, pipes, infrastructure provided. Then you have economic here that's looking into various from GDP. They're now the economists built the whole input-output model that will be part of the simulation model, and basically run in every time step the detailed analysis of the input-output interactions. So the details are coming. The details are coming now into. So what you see is just a graphical representation of the structure. This is a mathematical model in the background, but basically, you don't have any limitations here. How complex you build this structure is simply up to your knowledge and the time and resources that you would like to use. And the interactions, elements, all the elements you want to put, you put here. All the interactions you want to put, you put here. And that's what creates the complexity of the model. But this is all connected in this way how I define the measure, that resilience measure. And just to come back to your question on data, this is, and your kind of question, this is just a list of the data that we are now collecting, detailed data that we are collecting for the city of Vancouver. And you see we have a need for the time series data, where we'll be looking at details of the water infrastructure, coastal infrastructure, properties, maintenance data, response plans, emergency management plans, to physical, economic, social, health data, mobility, local disease data, and statistics. The city of Vancouver has a tremendous data bank that provides all the detailed information on, for example, health data, visits to doctors, what type of disease, what type of medication provided to each individual over a period of time. If we want, we can now build that component of the model so detailed that we can actually capture almost the level of individual in the city, all health aspects. The database is actually commercial, so you have to pay for that, and we will not be going to the level of each individual. We will be actually using some integrated information. So now coming back to your question of what will be the spatial unit, like if we utilize the existing data, we can go to each individual in the city. But we will not be doing that. Simply, from the other data may not be available there. So we are now in the probably in the range of so-called dissemination areas, which are defined by the Stats Canada as areas for which most of the socioeconomic data is collected and made available through the Stats Canada. And they are not defined as area. They're defined as area of the equal population number. Okay, so they may be different in size, and you can get the data for the city for different dissemination areas. And that we didn't make the final decision, but this is what we are kind of heading towards as a spatial resolution. And I would end here. In conclusions, I am trying to say that there are very important links between the disaster risk management, between climate change adaptation and sustainable development, that now the measure and looking into resilience as a really new concept to help us in reducing disaster risk may be really important for looking into the development options. The idea that the greatest improvement in the disaster risk management comes from the consideration of land use, urban and spatial planning, that means detailed consideration of the spatial variability, is also kind of addressed through the way how we find the measure. And obviously implementing this measure in the local context will give to that measure, I think, the specific characteristics of the locality that you're using. Thank you, and I'll be happy to chat.
The 4 cities that you mentioned here.
Yes.
Like, is Vancouver really in one of the 4 worst vulnerable cities in the world, or how specifically were those 4 cities?
No. The focus was finding out large coastal cities that may be affected by the disasters, various type of disasters. And that was the kind of criteria how we selected the cities. Vancouver is not. I mean, the comparison between the cities is not going to be done in this project. That's not the aim. The aim of the project is to develop the methodology how to assess the impacts on large coastal cities, and find a way or provide some advice what will be the best adaptation options, the impacts of climate change. If you look at the data, I mean, there's some interesting. Vancouver is a very, very seriously risky place. The large exposure, or the huge amount of money being, huge value being exposed to various vulnerabilities. The various sources of vulnerabilities, from Fraser flooding to earthquakes to storms and so on, can create havoc there. And that kind of led us to, and obviously being one of the largest centers in Canada, and the only large megacity, I would say, in Canada. So that was the reason. The funding is from IDRC, so the Canadian money is supporting this, and
we need a Canadian.
We need it.
A couple of, I guess, compliments and then a couple of comments. Yeah. First of all, I really like the idea that you are defining resilience. Up to now, it's kind of a vague, feel-good term. Second thing, I really like your concept there of putting together land use and spatial planning for disaster management. You'd think it would be an obvious no-brainer, but unfortunately, it is not. some of the things I think that I just like maybe some sort of an answer or two is you're taking some very qualitative measures there, quantifying them, and then juxtaposing them with a bunch of other, perhaps more easily quantifiable measures. I think there's a potential for error there that can creep in to the model. There's going to be an error in any model, but that's one of the things, is that once you start quantifying qualified measurements, people start to ascribe more, I guess, weight or value to them, and that's always a bit of a concern. So, you know, you're doing a quantification of social justice and then juxtaposing it with rainfall, and then integrating it in the calculus equation. At the end of it, people go, here's a mathematical, it's got to be right because it's a mathematical figure. Well, it's not, because some of the basis down there is qualitative. And I would think that would have to be pointed out to anyone using this model, that it's not mathematical certainty. No. The other thing is when you've got, as the same sort of thing, very different scales in your mapping, and one is, say, you know, a water or flooding, which can be done almost at the meter or centimeter or millimeter level, and you're juxtaposing that with other measures that are kilometers wide, scaling errors can come. So I think that, you know, if this is used as a tool, and it is strictly understood as a tool, and you play with those various measures to see how your resilience factor changes, it's extremely powerful. If it is looked at, as many tools are, as the be-all and end-all, and this is what my resilience factor is, that can be a real danger.
No, I fully agree with you. I fully agree with you on that. Okay, the first question on the kind of integrating various aspects of resilience. We are fully aware that the integration and what are we going to integrate will depend on the, you know, kind of focus that we select. And in our work, this is being done through this interdisciplinary team, where we have a group of social scientists that are looking and now providing us with a, you know, they decided to go with about 11 different indices that are measuring the social impact.
Thank God you didn't use the word holistic.
Yeah, no. The idea is that I am relying on the knowledge of experts in that particular field to judge, advise, and provide the input that's going to be the kind of best input for us. I'm trying that the concept methodologically does not have any limitations. However, whatever this concept calculates is going to be the consequence of what we put in, and that has to be very clearly presented, described, and developed. So on purpose, this is not going to be, let's say, when we develop a tool, I don't want that to call it, you know, city tool so that everyone can take it tomorrow and apply to Toronto, or London, or Hamilton. We are going to call it Vancouver City or Bangkok City. And even calling it Vancouver is going to be still limited to what we decided to include as the measures of the social impact, economic impact, health impacts, and so on. So it is clearly dependent on the level of kind of expertise and decisions that you make. And your second question was related to the scaling.
Yeah, when you're taking scales together.
Okay. We are pretty conscious of that. And in this particular approach, because we are doing this calculation, this equation that you call it, it's not equation, it's a system of equations, is being kind of calculated with a time stack. And that time stack has to very carefully take into consideration the scales. So the time step is adjusted to the smallest possible scale, so that we do not miss the variability that exists in a particular variable that's measured or changing over that very short scale versus the variable that is changing over a very long scale. So even in this kind of numerical approach that is behind these objects that I'm showing, we do very carefully take the scale into consideration. So I don't worry so much about that error. I am very much conscious about the first point that you made, that, you know, the model is here really based on our view, our conceptualization, our type of inputs, our type of, you know, impacts that, you know, we decide, or the group decided to. Dan?
Well, I just had the same comment or question about converting big quality indicators. So just out of curiosity, how would you what's sort of the plan to quantify religion, I guess, just as an example I saw it?
There are various ways. There are various ways how you do that. When we were developing the models for the flooding in the Red River, we were using the kind of religion as a way of measuring the coherence of the community. Okay, so based on a type of the religion, the size of the population, you have a different response to the disasters. And for example, coherence of the community, I'm not saying, this is going to be measured in the quantitative units. It will be on a scale between 0 and 10, and that's what we have done. And the interesting point, we were, for example, because we didn't have a lot of research being done in that area, then we started actually examining the sensitivity of the final results to that particular value. And we found very interesting things, that Mennonite communities responded to disaster much better because of that coherence than other communities. So there are ways. I'm not saying that's the best, but there are ways, and that's what we are going to proceed using here.
Just want to make a comment. When you deal with these kind of issues, I mean, the measure of any model should never be whether it's correct or not. The measure should always be, is it going to be useful? And I can see where this panel correctly could be.
Yeah. Yeah, this is we had as an objective when we wrote the proposal. This was not clear to me. I had an idea. I proposed the idea to look at the use approach and so on. But I really looked for something. Okay, so we want to come up with adaptation options or suggestions. If you start looking each area individually, the social, the economic, we are going to come up with really various suggestions. How these people who should be making decisions are going to use that? So we really, or I started looking for something that will integrate that message, that will give us opportunity to really run and analyze various adaptation options through, some kind of integrated measure. And the response is amazing. I must tell you, when we were presenting this in Vancouver, there were people from the Vancouver city, from different levels of government and so on, and the response was very, very positive. I was last 2 days in a by invitation workshop looking at the cities at University of Toronto, and I talked really a little bit about this measure. And I got amazing response. I mean, they are now connecting me to the UN agency that's looking at the large cities around the world, because they are looking for something like that tool that will be able to kind of integrate and assess the different options, different measures. And so let's hope it will work.
Could you talk a little bit about output? Well, I get the model and I get the links and I see the value, but in my head I'm having trouble getting it to. So I guess I have two questions. First is, who's the ideal user of this and who do you think will be embedded in it? The second part is, in my head as you were talking, I was instantly going to if-then kind of statements. So if the rain comes, then this will happen to the city of Vancouver or Laos, whatever. And is that the correct way that I should be thinking?
There are various ways you can use the tool and use the model. What we are proposing and what the project is focusing on is assistance to responsible levels of government for the cities. And among these 4 cities, we have a very different kind of responsibilities. In Vancouver, we had the presence of the local city government around the table, and they were asking questions and providing suggestions. And we had also the provincial representatives of the group. So there is a group climate adaptation group that's really looking into various adaptation options, what to do with the dikes, how to deal with the river, how to deal with the storm surges, and so on. So these are the potential uses. There is an agency that's responsible for the delta, and the director of the agency was also present at it. And they are seeing for that sub area the value in, having the tool like this. So I'm trying to say that there are various potential uses. One side, then you can use this. Our proposal is to evaluate various climate change adaptation options, and we come up for each of the cities with some kind of recommendations. But this tool can be used in a more kind of real-time response to a disaster. You can either simulate the performance of the emergency management services during the typhoon in Manila from last year. And because right now, there is a state that they're blaming each other. That the emergency services didn't work very well, number of lives lost, huge economic damage, and they want to find out. So I said, okay, let's simulate the event and see, what can be done if the things were dealt with in a different way and so on. So there are various ways, and therefore, various users that can benefit from the tools.
So are there literally outputs like geospatial data sets that show in land area?
I didn't answer that. I didn't answer that. Yeah, there are actually a couple of there are going to be reports in each of the areas that we are considering: health, economic, social, physical, and so on. And the key outputs of the model will be in this particular form, where we are going to kind of produce. This is the final graph that shows, for example, the resilience, the change of the resilience, health, economic, or any of the dimensions that we selected. This graph will be also available in the form of the map. And the map is not the same, it's not a static map. So it's going to be actually a set of maps, if you want. I would like that to be in a kind of animated form so that you can see the change and help immediately visualize where are the most kind of vulnerable areas, and possibly focus the attention to the areas of the city where we see the concentration of things. Now, this is the kind of output of the tool. We are planning to do the analysis of multiple options, multiple adaptation strategies. So the idea will be to produce the same output for different adaptation options, so that you can now compare if we focus on the physical infrastructure, or if we focus on the health services, or if we focus on the emergency management services, what is going to be the difference. So we are not going to, I wouldn't like to select one and say, okay, this is it. I would prefer to run this multiple simulation and present them as a various potential options, and then let the city of Vancouver together with the province of British Columbia decide what direction they want to go. They're now going into tremendous level of detail. They are now thinking and calculating how much is going to cost them to raise the dikes for so much in order to deal with the sea level rise. And I think they will have something a little bit more through this type of analysis than just focusing on, okay, so the sea level rise is going up with that level, and we need to, raise the dike so much. I want to show, is the raising the dike comparable to maybe changing the land use behind the dike, and, maybe moving the people, buying the land, or, doing certain things that may kind of change the need for, raising this infrastructure higher and higher and making it more expensive. So the idea will be to give the option, present the options, and my wish will be that one day they take the tool and they start doing this analysis, so that, our purpose is, we are doing research, and if we produce something that they find useful, that will be great. To
Daryl's comments about the importance that this can be applied, it can be used. I just want to comment on the dimension of time.
Yeah.
So in my sense, a lot of insurance companies are very focused on the near term, what's required so that things will work out next year, the next few years. The community I live in has a 5-year plan, and some communities have a 20-year plan dealing with development. Vancouver is one of, I think, only 3 cities in Canada that has a 100-year plan. Mm-hmm. And if you're looking at the next year or 5 years, variability in the climate is a bigger issue than change in the climate, the natural variability. To shows up all the time. But if you're looking in the 100-year time frame, the ability of Vancouver to use what you're doing is really powerful. This is ingrained in their long-term planning, that they know the city's been enormously transformed in the last 100 years, and a lot more change is coming. So this is a really good fit for Vancouver and how they're thinking about it. Do you intend to impose, when you're looking at the climate change part, a particular time frame, and how far out?
We already did that. We kind of committed in the proposal to look at the next 100 years, but with the three time segments, 2020, 2050, and 2100. So that's already kind of because this is a very traditional way of looking at the climate change impacts, and especially when you talk about sea level rise, which is a very slow process. These are kind of selected. However, what I would like, and we are right now, we have a group in Winnipeg that's kind of working on the inputs, especially rainfall, extreme rainfall events, and so on. I would like to have a set of large events, and possibly events that coincide, like a huge storm that comes with some very high wind. And we would like to actually demonstrate and use the tool on this particular event. The idea will be to demonstrate that the tool has much more power than only looking the long-term planning options, but also may assist in dealing with the event as it happens. The people in the earthquake area are doing something very interesting, and our tool can be easily applied to that. They would use the kind of simulation to run the very large number of earthquakes of different intensity. So by generating the output, then they process the output in a statistical form, and then they give you the probability, or they deal with the probability of the particular event and the consequences of that event. Something like that can be done, with this tool. But I think it will be more important to identify, especially for the, people like Philippines and so on, because they have a huge record of these very large, very important events, and for them is really responding to these events is probably the most efficient than, looking how are we going to respond in the long term to the changes that climate can generate.
Is this going to be open source at the end? Anyone can?
Yes, because this is a research. This is a federally.
The reason I'm asking is it seems to be very tweakable to other circumstances. For example, right now, if you look at the interface or lack of between insurance/underwriting, their risk assessments, business continuity, its risk assessment, and risk and insurance management, the people buy it, their risk assessment, it seems to be in many cases never the three of them or more of them will meet. And something like this actually might be useful in terms of merging those together, or at least getting them to interface to some extent.
That's kind of interesting, but the insurance people, okay, I am not, fully convinced, but I think for insurance people, use of a measure like resilience is, quite different compared to what you guys call risk. And that actuarial approach to risk is, kind of different. But I see the value, and I would like you to also see the possibility of kind of introducing definition like this, or conceptual definition like this, and possibly using for, integration of your. I think it's a really open, it's an open conceptual idea that can be implemented in various ways.
It's like anything else, it's a tool. There are huge dangers in using it, but if you understand the limitations of it, it becomes very, very useful. Yeah.
If I can move to draw things to a close, is there a last question or two? If everybody can join me in thanking Subodh for his time today.
Thank you.